is Nicole S. Today I have my 6-minute talk, and my topic of discussion is going to be the Brighton cycle. A little bit of an overview. Yes. We're going to go for the introduction, a little bit of the history, the main components, the important diagrams, assumptions for analysis of an ideal Brighton cycle, the important equations, the main application nowadays, conclusion, and, well, the references. The Brighton cycle is a thermodynamic cycle that describes the workings of a constant pressure heat engine. The original Brighton engine used a piston compressor and a piston expander, but more modern gas turbine also uses the Brighton cycle, which is also known as Joule cycle or Ericsson cycle. The engine cycle is named after George Brighton, the American engineer who developed it originally for the main use in piston engines. The Brighton cycle engines were some of the first internal combustion engines used for motive power. This one is like an overview of the Brighton cycle, development through history of the Brighton cycle. In 1872, the first Brighton walking beam engine, and 5 years after that, the Brighton 4-stroke air blast engine, and finally, 15 years after that, the first Brighton-powered automobile in the year of 1905. So in this slide, we have two different graphs. Yeah, the first one is an open gas turbine cycle. So fresh ambient air is absorbed by the compressor at state 1. Then the compressor compresses it at high temperature and high pressure at state 2. These high temperature gases with also fuel travel to the combustion chamber, and fuel is burned at a constant pressure. Then this mixture of gases go to the turbine at state 3, and they expand and produce work. And the exhaust gases go out through state 4. In the other hand, here, this one, it's an ideal Brighton cycle. It's a modeled version of the first one. So using standard air assumptions and replacing the combustion chamber with a constant pressure heat addition and replacing the exhaust ambient gases with a constant pressure heat rejection process, we can model the first graph and make it an ideal and also a closed system called the ideal Brighton cycle. The main diagrams, the PV and the TA's diagram. So from 1 to 2, we have isentropic constant pressure. From 2 to 3, we have constant pressure heat addition. From 3 to 4, we have isentropic expansion. And from 4 to 1, we have constant pressure heat rejection. In the ideal Brighton cycle, heat is added in the process from 2 to 3, and we can find the work in with the first formula. And also, heat is rejected at a constant pressure process from 4 to 1, and we can find the work out with this second formula. Yes. So to analyze the Brighton cycle, we have to analyze an ideal Brighton cycle, we have to make some important assumptions. Use air standard assumption and know that the turbine and compressor are always going to be isentropic, and there's going to be constant pressure heat addition from 2 to 3 and constant pressure heat rejection from 4 to 1. And also, of course, that it's going to be a closed system, not open system. The most important equations in the Brighton cycle are these ones. To find the temperature or pressure, we know that the process from 1 to 2 and 3 to 4 are isentropic. That's why we can use that relation. And then since the pressure at state 2 equals the pressure at state 3, and the pressure at state 1 equals the pressure at state 1, 4 equals the pressure at state 1, we can use also that formula to find the temperature. And considering all the relationships above, we can find a formula for the efficiency of the Brighton cycle, which is the last formula in there. And, well, the best known application of the Brighton cycle, as we know, is the jet engine. All jet engines and gas turbines are heat engines that convert thermal energy into useful work. The main application is in producing compressed air and combustion products, which are then accelerated to provide reaction propulsion. And yeah, this is one of the most known applications of jet engines. And to conclude, how can we increase the performance of the Brayton cycle to model it as an ideal Brayton cycle? We can increase the turbine inlet temperatures. Also, we can increase the turbine and compressor efficiency. And we can do different types of modifications to the original Brayton cycle. For example, regeneration, and also we can have multiple stage compression with intercooling and multiple stage expansion with reheating. And that's my references. That's everything I have, and thank you so much. Do you have any questions?